Today I want to show you our research in CMOS circuit integrated intelligent microscopic structures. So basically, we are studying microscale structures.
Sure. Sorry, there's a big noise from your side. I'm not sure how did you hear that? Or say hi. Did you hear there's a big sound? Or is it from my?
Yes, I hear that.
Okay.
I also hearing.
Let me just to use the microphone.
Sorry. I think the reason
the microphone of my computer, it is better.
Or are you using a laptop? I think maybe the fan of your laptop, but that's okay. Yeah, just to let you know, so you can start again, but there's a big sound actually from your side.
Okay, that's interesting. It's still
better. Right. There's still a sound, right?
Like airplane, like airplanes taking off.
Right. So actually, I suspect it's because of the fan. I'm not sure if you experienced this before.
Is it this video on slides going on? Is there any noise from there or?
Let me try. Will this be better?
Yeah, I think this is slightly better. So you can start again, and we will cut this video. All right. Thank you very much.
Okay. Cool. Okay. So my topic today is CMOS integrated intelligent microscopic structures. So basically, we are studying microscale structures in the order of 100 micrometer or smaller. So in this scale, you cannot use your eye to see them. You have to use a microscope. So that's why we call them microscopic structures. And also, we are embedding intelligence by integrating CMOS circuit with our structures. Okay, I will show you how we make them later. But overall, when we think of a smart structure or robots in different scale, for example, in meter scale, we have made all these different structures. For example, this Boston Dynamics robotic dog. It can work, it can run, it can also sense the local environment and make decisions. Of course, on the other hand, we have many other things like this kind of factory robots. They can be programmed to achieve all these different and difficult tasks. For example, even assembling a car. Now let's imagine a case. If we can shrink down some of this machine to the order of like tens of micrometer, what we can do? Basically, we will get something like this. Of course, this is an imaginary image, but as you can see, if the size of our machine is comparable to the cell size, we can do single cell manipulations, just like what we use the big robots to deal with our daily things. For example, it can pick up a cell and do some surgery for this cell. For example, just injecting something to the cell and then just release the cell and go to the next cell. Of course, as you can see that the size of one device is only about like tens of micrometer. So it's very easy for us to have like millions of these devices working together to achieve some very complex functions in a very efficient way. So that's our goal. The question is that have people made this kind of things or not? The answer is sort of. In many of these movies, we have a lot of these smart microscopic structures. For example, this Marvel movie, Ant-Man. Ant-Man is riding on some microorganisms and it has red blood cells surrounding it. We know the scale of red blood cell is basically several micrometers. So this is basically the size we want to study. So as a researcher, we can ask ourselves, whether we can make this kind of things or not. Or another question is that in order to make this kind of structures, what do we need to do? Okay, generally, if we look at all these smart structures, no matter their sizes, they basically have two main components. The first one is the brain, the second one is the leg. Brain led it to process the information and make decisions. Legs led it to interact with the local environment, either by moving itself or change the local environment in some way. Okay, if we look at the brain, basically people is doing pretty well. For example, the first transistor was made in 1947. It's very big. However, after like 75 years, we can, like, this is the M2 chip from Apple this year. We can already build 20 billion transistors in the order of 1 centimeter. So you can imagine that even we shrink down this scale into, for example, tens of micrometer, we can still get like millions of these small transistors in our brain. This is far enough for us to do most of this simple information processing, decision making. Okay, we can borrow this semiconductor technology to use them as a brain of our structure. How about the legs? If you search for like the papers or literatures, you can find few literatures working in this region. The main reason is that if you want a structure in the whole size is in the order of tens of micrometer, you want the actuation ability of your legs or actuators at least 1 or 2 orders smaller compared to your overall structure. So in our case, we want this actuator to be able to, for example, bend from a flat state to a grounded state in the radius curvature at most like several micrometer. That's very hard. We can do a simple estimation. For example, for bending, the string is basically in the order of thickness divided by radius curvature. So if you want the radius curvature in, for example, 1 micrometer, and your thickness is like 10 nanometer, the string is 1%. Like for some polymer, that's not a big string, but for metals, this basically reaches the limit. So this is a very hard problem. And the next thing we want to solve is that assume we have the brain, assume we can somehow find the right actuation system, how we can actually integrate the brain and the legs together and actually make this kind of smart structures. Okay, these are the two things I want to talk to you today. Let's start from the legs. Okay, let's first see what nature do. For example, this is the swimming of a paramecium cell. And also, if you search for the locomotion of most microorganisms, they use the same mechanism, cilia beating. And the cilia is basically the small hair-like structures covering its body. As you can see here, as the paramecium cell swimming, you can see these hair-like structures are beating in a specific pattern, and this kind of beating facilitates the swimming of most microorganisms. So in terms of legs or actuators, what we need to do is basically to do something similar. We want some microscale actuators, and it can either pump the fluid or let our microscale structure move. Let's first look at the existing systems. For example, people are using pressure-driven actuators. They have valves, they have pressures, and they can change the pressures in different valves. You can get uniform beating, and you can also change the beating pattern. However, for this kind of method, it's very hard to make them into micrometer scale. Also, there are studies using the electrostatic actuation. You change the voltage in a capacitor, then you have some displacement. This method, we can make them into micrometer scale, and as you can see, they can also do the pumping. The main issue for this method is that they basically need a high voltage. usually around 100 volts. So this makes it incompatible with the water-based solution, and also makes it incompatible with CMOS circuit, because we know usually CMOS circuit only supports voltage in the order of 1 volt. Also, some other methods, for example, this is a very popular method in recent years. People using magnetic materials and make them as the shape of our artificial cilia. Then they apply an external magnetic field, for example, rotating magnetic field. Then you can get some actuation like this. You can make them very small, and as you can see here, you can also pump the fluid. The main issue for this method is that when you apply an external field, you apply the field to all your structures. You can not specify which actuator you want to actuate. You cannot differentiate them. And of course, magnetic method is not compatible with CMOS circuit. One thing I do want to say is that all these researchers are great research. They just does not meet with our requirements. Okay, based on all these considerations, the actuator we choose is the surface electrochemical actuator that our group developed. And in terms of actuation ability, we have proved in this paper that this is basically the best actuator in terms of all these literatures and papers we can find. The mechanism is shown here. Our actuator has 2 layers of thin metal. The total thickness is around 10 nanometer, and the active layer is platinum, and passive layer is titanium, and it uses the electrochemical reaction of platinum to do the actuation. So we have 2 parts, and the actuator part and the reference electrode. The whole system is immersed in some water-based solution, and if we apply a positive voltage to our actuator, for example, positive 1 volt, the platinum surface will be oxidized. This oxidation will cause some surface strain, and as you can see, we have a passive layer on the other side, so only one side will have surface strain. This asymmetric expansion will cause the bending or unbending of our actuator. The good thing for this actuator is that when we apply a negative voltage, for example, negative 0.2 volts, we can remove this oxidation layer, so this actuator can go back to its original position. So as you can see, when we apply an oscillating voltage, our actuator will also oscillate. The first question we want to answer is that whether this actuator can do work, either pump the fluid or move our microstructures or not. The answer is yes. So if you look at this left video, as you can see that our actuators are oscillating in the middle, and if you look at all these small particles, they are going from bottom to the top. So at least we can claim that our actuator can pump the fluid unidirectionally. And in the right, we also characterized the pumping performance by changing the geometry such as the length and also the actuation frequency. As you can see, usually the pumping velocity is like tenths of micrometer per second, and this length is comparable to our cilia body length. And also, if you search like different papers, this is also an average level for cilia pumping in micrometer scale. Cool. And there's actually some fluid mechanics behind it, because we know that this is in micrometer scale, and we also know that if we calculate the Reynolds number, it's usually in the order of 10 to -3. So we cannot use the way we usually use in meter scale, like inertia-based method to do pumping. There has to be some other way to break a symmetry and get some net flows. Let's at first see what nature do. This is the trajectory of a cilia in nature. As you can see that they have different trajectories in the first half period and in the second half period. In the first half period, it's much more straight. In the second half period, it's much more curved. So this means it pumps more fluid to the right in the first half period, and it ejects less fluid back in the second half period. So in an actuation cycle, you will have some fluid pumped to the right. That's how we can achieve pumping in micrometer scale. And if we look at our actuator, it's actually the same. This covered area basically indicates the difference between the first half period and the second half period. And we have proved that basically the size of this area is proportional to your pumping performance, basically pumping velocity. And we also did a fluid dynamic simulation. We used resistive force theory to model the fluid force. We used the beam theory to model our cilia. As you can see that the trajectory from simulation and the experiment matches very well. I can briefly explain the physics behind it. The reason is that when this actuator is oscillating in fluid, it has two forces. The first force is the fluid force. The second force is the elastic force. So when we design this system, we let these two forces comparable with each other. So the fluid force can also influence the shape of our actuator. Because in the first half period and in the second half period, the fluid force is in different directions. So this is why we get different shapes in the first half period and in the second half period. Okay, as I have explained, this is basic mechanisms, but still this is not perfect because as you can see, this kind of symmetry breaking depends on the hydrodynamic coupling. This is something we cannot control. And also, as you can see that this covered area is not that large because this kind of coupling is basically a high order term. So if there's some way we can do to make it better, make it more controllable, or make it more efficient. So in order to do this, we make a new design. At this new design, we have two independently controlled hinges, and we apply a voltage with same frequency and with a phase delay. So in one actuation loop, you will have four stages, and this shaded area basically indicates the amount of asymmetry. As you can see that this area is much larger compared to our previous design. And of course, we have measured the pumping distance per cycle. This new design is actually better compared to our previous design. We also captured several frames from the video we took. As you can see that these particles are actually going from the bottom to top. To help you understand it better, we also have simulation to show the pumping. Something like this. As you can see, they are going from left to right. Okay, this is the mechanism. Now I want to show you what we can do using this new actuator. First, because this is an electrical actuation, so the difference between electrical actuation and something like magnetic actuation is that we can selectively actuate the region we want. For example, here I built a building block with 8 small arrays. Each array we can independently control them. Then I selectively actuate 4 of these 8 arrays. Then I get an extensional flow. The flow goes in from the bottom and the top goes out from the left and right. And of course, as you can see, if we just choose different actuated arrays, we can get different flow geometries. Here, we not only have the experimental result, we also made a simulation to help us understand the 3D flow profile. And of course, the average simulation matches very well with our experimental results. And as I mentioned, we can get all these different flow geometries like flow expansion, flow transportation, flow turning. Great. Then what we can do is just to put these building blocks together to make a big metasurface. Here you see a metasurface with 64 independently controlled small arrays. So it can basically give us a huge number of flow patterns in one device. And also I made a software, makes it very straightforward to control. We generate voltage signals from lab view and send these signals to the hardware, to the hardware and go to our devices. So you can just change the voltage levels in lab view, and then you will get different flow patterns. Now I want to show you several examples. For example, we can get two flow geometries in one metasurface. We can also get something like flow rotation, flow transportation. The flow can even like split at first, then merge again. These are all the things we can do in one device. And if we use this device, we can already have a lot of applications, manipulate fluid, manipulate chemicals. However, in some cases, we actually want to make it better because, as you can see, we still need a setup. We need a computer, we need software. These are very big things. We do not want to carry them all the time. In many cases, we just want our tiny actuators work by itself, and we also want it to be intelligent. So how we can do this? In order to do this, we made a lot of these optically powered CMOS circuits. As you can see here, the basic process is that we cooperate with our collaborators at Cornell, and then we design all these circuits, and then we send out our design to the external foundries. Then the foundry make all these CMOS circuits for us, then send them back as several 8-inch wafers. Then we dice them and do all the post-processing, photolithography, testing, measurements, and if it works, we can get our devices. The good thing for this device is that, as you can see, the size of one device is very tiny, about tens of micrometers. So we can basically have millions of these tiny devices in one wafer. The cost of one device will be very cheap, like 1 cent or even less. This is a huge advantage if we want to do the future commercialization. Okay, let me show you what we can do based on this kind of optically powered CMOS circuits. This is one example of a clock circuit. As you can see, it basically has two parts, the top parts and the bottom parts. The top parts are the powering parts. When we shine light on this photovoltaics, it can power our actuator and power our circuit. And the bottom part is a clock circuit. We have an oscillator that generates oscillating voltage. Then we divide this oscillating frequency to the range we want, and then we generate all these different phases. So basically what it can give us is that when we shine a constant light in an intensity comparable to sunlight, we can get oscillating voltage signals with certain phase delays. Okay, if we are lucky and this works, and then we make all the post-processing and also all the post-processing are perfect, then we integrate our actuators on them, and then we release them to the testing. We can basically get something like this. As you can see here, the right part is our circuit. We shine light on all of them, and then as you can see, there are several arrays of our actuators. They are oscillating with some certain phase delays. Actually, this kind of wave-like actuation is very important as well in nature. It also shows up in the video I just showed to you, the swimming of a paramecium cell. As you can see, during the swimming, all these cilia, they are beating in some wave-like patterns. This is actually what we are showing here. Of course, we measured the pumping velocity by changing the phase delays, and we also demonstrated the same idea because the same conclusion as other people. As you can see here, if our phase delay is in some intermediate value, we got the best pumping velocity. Okay, this is something we can do to integrate the CMOS circuit with the artificial cilia. As you can see here, we do not release our device. All of them are still in the substrate. Then we change the local fluid environment. As you can see, there are many other things we can do. For example, we can put several legs around our circuit and we release our device. Then we shine light. Our circuit will just become a walking robot. Then we can get something like this. We use the same circuit, we use the same actuator, we release this device, we shine light, the actuator will oscillate, then the robot will work. This is a project led by my colleague Michael. I'm also involved in this project. So these are all the things we can do. As you can see that this is just the basic clock circuit. We can also make a lot of other circuits. For example, this is another circuit we have built. In this circuit, we can program other things like the frequency and the phase of each output. As you can see here, it has two optical inputs. The first one controls the frequency of our actuator. When we change the frequency of this clock input, we also change the frequency of the actuator. And the second one is the power, and in this power, it also has embedded programming signals. If we look at a block diagram here, there is our power signal goes to a scan train that can count the number of small pulses embedded in the power signal. Then this number will go to a multiplexer and use this number to choose the right phase we want to get. And then all this electronic signal will go to our actuator. We will shift this voltage signal to the range we want. So here we can program all the things using lights. The advantage of this this way is that we do not need to use wires to go from our computer and then go to our actuator. We just need to shine light on it and it can work by itself. If we want to change the pattern, we just use the pulse light to get all the different patterns we want. Okay, of course, there are many things we can do. This is just an example. This is summary. These are basically the three papers I mentioned today, and it's very interesting that we got covers for all of these three papers. And I think and currently we are also doing more things like making more circuit designs, making more robotic designs, and also thinking of new actuators. Okay, this is basically what I have for today. Thank you.